On a cold January day in 1986, the Space Shuttle Challenger blew apart high above Kennedy Space Center on Cape Canaveral, just 73 seconds after launch. A rubber seal called an O-ring had failed, and a plume of fire leaked out of the solid fuel booster, igniting the gigantic fuel tank. With millions of people tuned in live on TV, Americans watched in disbelief as a sinister white plume streaked across the sky, and 7 astronauts, including New Hampshire high school teacher Krista McAuliffe, plummeted helplessly 20,000 meters to their deaths. America was plunged into uncertainty and grief, and questioned NASA's ability to manage the immensely complex space program effectively.
He said, I would not recommend that we launch below 53 degrees Fahrenheit. And that was primarily based on the experience we'd had 1 year earlier that concerned us. And frankly, I was shocked because I felt that that was a slam dunk. They would accept that and just postpone the launch. They immediately started questioning the basis for making such a recommendation based on the material presented.
The single message that came out in a direct quote to me from one of the most senior administrators in NASA when I said, we're going to lose one of these shuttles, and I said that 3 months before Challenger, said to me, our job is to launch on time, every time. And it was one of those hairs on the back of the neck moment when I realized they're not listening.
When a chastened NASA emerged from the tragedy, shuttle flights resumed. The shuttle pushed the frontiers of technology to the utter limits, and this incredibly complex machine continued flying for another quarter of a century, with astronauts from around the world aboard.
I almost thought, I'm the weak link. I was the one who had to perform at the level needed to be up to the standard of the others. My work was as important as the others. I had to trust the others, the astronauts who were with me, but also those setting up the launch, those who followed the operations. And at the same time, they had to trust me. Jokingly, I thought, I don't care if the shuttle blows up, as long as it's not my fault.
Basta che non sono stato io.
A small group of brave engineers, analysts, and astronauts risked their careers so that the managerial errors behind the Challenger disaster never happened again. It took 2 years before the problem was fixed and the next shuttle launched. One of the last Space Shuttle missions is about to launch. This complex machine has completed 135 missions. Italy's first astronaut, Paolo Nespoli, flew on the Shuttle mission 120 in 2007. Like all but 2 missions, it was a successful flight where nothing went wrong. Although he was trained to be prepared for anything. Literally, the tiniest error could mean catastrophe.
As crew, we had serious problems. Our training was very tough, very serious. For example, at the time of launch, there were a number of malfunctions that could happen, and according to how they interacted between each other, a simple and a stupid thing could have a knock-on effect and lead to the destruction of the vehicle. As a member of the crew, you had to understand all these things. And there was this kind of game, let's call it a game, between the instructors who wanted to kill you and you, who responded successfully to all these provocations.
January 1986. Space Shuttle Challenger was originally set to launch from Kennedy Space Center on January the 22nd, 1986. But bad weather led to delays. The launch slipped from January 23rd, then 24th, and then 25th. Another weather delay and a technical problem with one of the door hatches pushed the launch back another 2 days. On January the 28th, the weather was still colder than usual for launching the shuttle. Alan MacDonald represented the Utah-based builder of the solid-fuel rocket boosters, Morton Thiokol, on site.
I can remember walking out of the Launch Control Center to my car after that, and I never felt wind so strong, and the sand was blowing into my contact lenses, and it actually stopped me at times, and I'd have to lean forward. I got to my car to go to my friend's house, and I wasn't there very long, and I got a phone call. The phone call was a fellow by the name of Bob Ebling that worked for me. And he said, Al, he says, we just been notified that some meteorologist in Orlando said, you know, these strong winds that canceled our launch today, that there's a real cold front behind that. And by tomorrow morning, it may be down as close as 18 degrees Fahrenheit as cold. I said, good grief, I'm really worried about whether these O-ring seals will operate at all at those kind of temperatures.
Back in Utah, the engineers were so worried about the effect of the cold on the O-rings that they asked MacDonald to get more detailed weather reports from NASA.
I said, fine, I'll get that information for you. But when I get it, here's what I want you to do. I want you to provide that to the engineers. I want them to put together a presentation of what we know and don't know, what our concerns are. And at the end of that presentation, I want you to make sure that the Vice President of Engineering comes on and makes a recommendation. What is the lowest temperature it is safe to launch? We have to do that.
Alan MacDonald got all the parties on board for a teleconference between engineers in Utah, those in Marshall Space Center in Huntsville, Alabama, and NASA management at Cape Canaveral. More than a dozen engineers faxed their charts and made a clear and unanimous recommendation. The shuttle should not be launched if the temperature was below 53 degrees Fahrenheit or 11.6 degrees Celsius, due to concerns about how the O-rings would perform.
At the end of their presentation, the Vice President of Engineering, a fellow by the name of Mr. Bob Lund, got on the network and said, based on what his engineers have presented here this evening, because they had to fax all those charts to both Huntsville and also to the Cape, he said, I would not recommend that we launch below 53 degrees Fahrenheit. And that was primarily based on the experience we'd had 1 year earlier that concerned us. And frankly, I was shocked because I felt that that was a slam dunk. They would accept that and just postpone the launch. They immediately started questioning the basis for making such a recommendation based on the material presented.
Then, the unthinkable happened. Several top executives vetoed the engineers' recommendation in an offline caucus, giving NASA the green light to launch Challenger at a temperature that was just 38 degrees Fahrenheit, 3 degrees Celsius. A few engineers protested, but were overruled, due in part to concerns about losing lucrative government contracts if the launch schedule were to fall further behind. NASA wanted the recommendation faxed to them in writing. Alan refused.
I did the smartest thing I ever did in my life. I told NASA I would not sign that recommendation. I feel we're taking risks that we should not take. It'll have to come from the plant, if it comes from anybody, but not me.
The O-rings were not the only concern. Alan told those gathered at the teleconference that high winds were gusting up to 70 knots and there was ice everywhere. All the while, NASA officials were pressing for the facts from Morton Thiokol.
At that point in time, they said, well, Al, you've brought up all these concerns that aren't really should be your concerns, but we'll pass them on in an advisory capacity only. Where is the fax from your boss?
The next day, the ice teams were busy knocking icicles off the shuttle and using an infrared pyrometer gun to get temperature readings that were entered into NASA logbooks. A later review of those logs showed the temperature near the failed solid rocket booster was below 28 degrees, or minus 2 degrees Celsius, much colder than the ambient air temperature of 31 degrees Fahrenheit, just below freezing point. It was shaded from the sun and exposed to westerly winds. In the meantime, the astronauts were preparing for launch, a complicated process with strict protocols to follow. Paolo Nespoli flew on the shuttle in 2007.
Qualche ora prima del lancio, 5-6 ore prima del lancio.
A few hours before the launch, 5 or 6 hours before launch, it's time to get dressed. We launch or launched with what is called a launch and entry suit, which is a pressurized suit that allows the crew to stay alive in case of loss of pressure inside the shuttle. So it began to be complicated with gloves, a helmet. To speak, you needed to use a communication system, which means that if 7 people all speak at the same time, it becomes incomprehensible. So you need discipline in terms of who speaks, what they say. So we put on the suit in the quarantine area. There are protocols to check the resistance to pressure of the suit. And from there, you go to the launch ramp using a special vehicle.
E da lì si esce con un veicolo speciale, si va alla rampa di lancio.
When I walked in, I heard the radio say it was 22 degrees Fahrenheit. I was carrying my briefcase and my headset because I was in the adjacent contractor support area of the Launch Control Center. And I went up to my computer console that monitors all the data that comes from the solid rocket boosters, but it also has an inset of NASA Select video of the launch. But it also has several other options for cameras to look at on the launch pad. So I started looking at these cameras and I saw this ice all over the place. Now, well, they're not going to launch this thing today, obviously.
But the comforting facts had arrived from Morton Thiokol bosses recommending NASA to proceed with the launch. The countdown was on. There was no turning back.
I was worried that it was cold, and I really felt that if the boosters would fail because of that issue of not sealing in the joint because it was too cold, that would all happen in the first 6 or 7 tenths of a second, and we would see a leak sprung, and that the whole thing would probably explode by the time it cleared the tower.
At 11:38, the shuttle lifted off.
9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
The relief at the successful liftoff of the Challenger space shuttle in January 1986 was short-lived, however.
It cleared the tower. I breathed a great sigh of relief. And it wasn't until 73 seconds later that this big explosion occurred.
Throttling up, 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up.
And everyone in there was shocked, including me, that I knew that wasn't survivable. And I could hear people sobbing actually in the background because I had my headset on, and all I could hear from the network was RTLS, RTLS from the Capcom, which meant return to launch site, return to launch site.
The 7 Challenger astronauts, Commander Dick Scobie, pilot Michael Smith, mission specialists Judy Resnick, Ellison Anizuka, Ronald McNair, and payload specialists Krista McAuliffe and Gregory Jarvis, would never return to the launch site. For 2 hours, Mission Control was in top-secret lockdown as NASA scrambled to set up a failure team to find out what had gone wrong at 14,000 meters above the launch platform.
The Vice President Bush called and said that he was getting on a plane and he was going to come and talk to everyone in the control room that evening, and he did. And he basically said that, you know, it's a horrible, tragic accident. We need to get to the bottom of it, figure out what happened so it doesn't happen again. But this is not going to stop the Space Shuttle program. We're going to get back to safe flight as soon as we can. And this is the team that's going to have to do it.
The tragedy was that a whole structure was set up in the United States whereby children sat and were assembled before their television screens right across the United States to watch the launch of Challenger. And Krista McAuliffe, their teacher in space, who was scheduled to carry out lessons from orbit while she was in space.
And I want to say something to the school children of America who were watching the live coverage of the shuttle's takeoff. I know it's hard to understand, but sometimes painful things like this happen. It's all part of the process of exploration and discovery. It's all part of taking a chance and expanding man's horizons. The future doesn't belong to the faint-hearted. It belongs to the brave.
The next day, the failure team gathered at Marshall Space Flight Center in Huntsville, Alabama. Though he hoped it was something else, McDonald suspected O-ring failure. The convincing and critical piece of data was a few seconds of film showing a puff of black smoke in the right booster in one of the aft section field joints.
My heart about sank. And I'll never forget calling home that evening, telling my wife that canceled plans, I wasn't going to be there. I didn't know how long I was going to be. And I knew I needed to do that, but my 3-year-old daughter answered the telephone, Megan, and she says, "Daddy, when are you coming home?" And I says, "Pretty soon, Megan, pretty soon." She says, "Daddy, when is the space shuttle going to go up?" And I couldn't answer, because she knew her daddy always came home after the space shuttle went up. And I said, "Pretty soon, Megan, pretty soon."
But how did NASA get to this low point in its history after the glory years of Apollo? And why did it take so many risks with the shuttle? NASA scientists were already studying plans to build a reusable space shuttle at the time the planning for the Apollo moon mission was in full swing. The goal was to drastically lower the cost of space flight. A program to build it was formally launched on January the 5th, 1972 by President Nixon.
When the shuttle was initially approved by Congress, NASA wanted as many users to get on board to justify it. And the Air Force was a big, powerful lobby in any space project. And so NASA went to the Air Force and said, "You can use the shuttle. We can replace all your conventional ballistic rockets for launching your military payloads, your spy satellites, your military weather satellites, your navigation satellites, and so on." The Air Force signed into this and said, "We can do amazing things if we have this enormous vehicle that can fly to any landing site across the United States on any orbit that it comes back from."
In the 4 decades of the United States Space Shuttle program, 355 men and women flew on 5 space shuttles in 135 missions. They launched cutting-edge satellites, sent spacecraft to explore Venus, Jupiter, and other far reaches of outer space, and contributed to building the International Space Station. Paolo Nespoli flew on the shuttle in 2007 to deliver the Harmony Utility Hub, the station's permanent living headquarters for astronauts.
The shuttle
was an extremely complex vehicle. As an engineer, as I began studying the shuttle systems to become mission specialist, I thought to myself, goodness, this is an extremely advanced vehicle. It was designed in the 1970s, but it is extremely complex. It looks as though it was designed to be complex. They couldn't design something simple. They designed it to use the full range of the engineer's imagination, using all their capacity. But at the end of the day, they didn't realize that they built such a complex machine with such complex interactions between systems that they were impossible to
così
manage.
complesse che non potevano essere gestite.
Building the shuttle proved more complex and expensive than expected. The US Air Force, now NASA's main client, required a winged aircraft that a pilot could maneuver, protected by heat-absorbent tiles that did not have to be replaced for every mission. To launch satellites, the Air Force also demanded a huge cargo bay. The end result was a spaceplane that weighed more than 20,000 metric tons. The three main engines located aft of the cargo bay were fueled by a mix of liquid oxygen and liquid hydrogen. Each produced 200,000 kilos of thrust. They were gimbaled to control pitch, yaw, and roll.
The liquid fuel engines were soft engines. In fact, they were ignited 6 or 7 seconds before launch because they had to gain pressure. There were these turbine turbo pumps that went and when these started, you'd feel the shuttle alive. It moved, and inside the cabin, you'd feel this movement because the engines had enough power to move the shuttle, but not to lift it off. At T0, the moment of launch, explosive bolts were ignited that kept the shuttle attached to the launch platform. They were ignited.
Piantato sulla piattaforma di lancio, questi venivano fatti esplodere.
The solid fuel boosters were ignited that are incredibly powerful, with such thrust that they give all their power in a millisecond. And at that moment, you feel a train hit your back, and suddenly you are thrown upwards.
Sentivi un treno che ti arrivava sulla schiena e improvvisamente ti buttava verso l'alto.
The largest solid propellant motors ever built, and the first to ever be used on a manned spacecraft, with a power pack that kicked the shuttle into space. Each booster was made of 11 individual weld-free steel segments, joined together with steel pins. Once assembled, each booster measured 35 meters long and 3.5 meters in diameter. The more than 450,000 kilos of propellant inside burned at a temperature of 3,200 degrees Celsius and generated a liftoff thrust of 1.2 million kilos. The boosters burned for 2 minutes in parallel with the main engines during the initial ascent, pushing the shuttle out of the atmosphere. But then, at about 39,000 meters above the Earth, the boosters separated from the external tank and fell into the Atlantic Ocean under huge parachutes, to be recovered and returned for reuse.
The equivalent of the energy contained in a shuttle is equivalent to a small atom bomb. So much so that they clear that area for kilometers and kilometers around the launch pad. Because if anything happens, everything is razed to the ground. Where are you? Sitting on the atom bomb that is about to explode in a controlled fashion, shooting all this energy downwards and pushing, launching the shuttle into space.
The external tank weighed 35,000 kilos and contained 725,000 kilos of liquid oxygen and 102,000 kilos of liquid hydrogen. It is the only part of the shuttle not reused after each flight. Thrusters were located in the nose and tail segments, while orbiter maneuver pods located in blisters on either side of the vertical tail surface provided power to get the shuttle to rendezvous and onto the re-entry path. There was space for 7 to 8 crew members, the most ever to travel in space, housed in the pressurized nose section that combined oxygen and nitrogen to create a shirt-sleeve environment for the 2-week average duration of the mission. As NASA entered the digital era, avionics changed radically, with computers managing data from dozens of sensors in the fuselage and wings. The NASA Space Shuttle program was well underway by the 1970s and bringing thousands of jobs to communities across the country. Tenders went out, and the winning contractor for the solid fuel boosters of the shuttle was Morton Thiokol, based just north of the small town of Ogden, Utah. Much of the research and development behind the United States' most advanced weapons and satellite delivery systems and rocket research was happening here, in the remote, sage-covered hills along Highway 83, near the salt-encrusted edges of the Great Salt Lake. Today, near the sprawling former Morton Thiokol production site, a road sign points visitors to a rocket garden outside the plant. For 26 years, portions of the shuttle's solid fuel rockets were researched, developed, and constructed here, under the oversight of Alan McDonald.
Well, the shuttle boosters were so large that we had to make them into segments and send the pieces as a segment to the Cape in Florida on a rail car. And there's only a couple of lines that you can get to Kennedy without hitting bridges, because they're about the largest thing you can put on a train. They're over 12 feet in diameter, each the sections, and there's 4 of them you have to put together. You just kind of stack them up like beer cans on the mobile launch platform. They're sent down by rail. And when they are received down there and ready for assembly on the mobile launch platform, because they're stacking on top of it, there's a joint that is made to assemble the entire rocket booster. But in that joint, we have to make sure that the gases can't escape.
These enormous shock waves that go through the booster cause it to expand and then to bounce back. So they bow out and then bounce, and you cannot see this. It's fractional, but it's very meaningful inside those joints. And they realized that there could be flexing and movement inside those joints that would cause gas to escape between the sections in the field joints that the propellant was burning. So at ignition, you get this great convulsion of a great enormous button. It would literally push, like pushing your elbows out on balloons. It would cause it, and then the balloons push back. So the sheer strength of the steel casing caused it to hold up and stabilize at that point. But in the critical area where the gas is shooting through the gap, you need to have 2 O-rings that go right around the joint to seal it.
During launch, the joint had to withstand pressures of more than 63 kilos per square centimeter and temperatures of more than 530 degrees Celsius. The O-ring provided the pressure resistance, while a zinc chromate putty applied to the interior of the joint provided the temperature resistance.
And it's what we call a tang and clevis joint, much like a tongue and groove in a hardwood floor. And because of that, we have to put something to seal the gases in. And the way we do that, we have 2 O-ring seals, much like you have washers in your hose or in your sink to prevent the water from leaking. This prevents the gases from getting out. And the reason there's 2 of them is that this was considered such a critical function, we had to provide redundancy wherever it was possible to do that. In case one of them failed, the other one then acted as a backup to prevent failure, because it was well known that any gas leak out of one of these joints would be catastrophic.
The O-rings that sealed the joints were made of a vulcanized rubber substance called Viton. But from the very beginning of the shuttle program, engineers were concerned about the performance of the O-rings and their ability to seal properly in cold temperatures.
The Viton O-ring is a fluorocarbon rubber, and one of its primary characteristics, why it was selected for this type of an application, is that it is very tough. It was really worried that these huge segments that weigh over 300,000 pounds each, when they're pulled together, that if they were not quite lined up properly, it may cut the O-ring during the assembly. And we found that this material was by far the best to resist that from ever happening. So it was a rubber material, but it was a fairly hard rubber material.
It was vital that the seal remain efficient for the whole of the flight. But temperature could change the behavior of this basic material, which worried engineers early on.
One of the characteristics of any rubber material is that since we're using them in a compressed state, we're squeezing them into these joints in a compressed state, and we do that because we knew that that joint opened a little bit when it pressurized. So there was enough compression in the O-ring squeezed in there that when it did open, it would maintain contact with the other surface as it was opened. Now, the characteristic of doing that is called resiliency of material. It's kind of like a wet sponge. You take a wet sponge and you put your finger on it and you start to release it. You'll notice your finger stays right with the sponge, but you take that sponge and throw it into the freezer and take it out and push your finger on it. It leaves a dent and it won't recover until it finally warms up.
Engineers analyzing the shuttle and its boosters upon each return from space had noticed erosion of some O-rings and menacing black soot around the O-rings, a phenomenon they called blow-by, because it meant hot gases were leaking and blowing by the joint.
In that final year, full year of Shuttle, 5 of the 7 Shuttle flights demonstrated blow-throughs on these boosters. We'd never have known this if those boosters hadn't been recovered and inspected in detail for post-flight analysis. But the engineers to a man said, we are playing with dice and we're running across a freeway blindfold in rush hour and we're going to lose some crews.
It actually was noted a problem with these joints way back into the second flight of the shuttle, STS-2, where in disassembly of one of the field joints, they noted some erosion on the O-ring, which meant that gas got down there to burn it. And the way the joint was designed, we actually had material ahead of the joint in that gap. It was really a zinc chromate putty loaded with asbestos to try to thermally isolate the O-ring so we'd never see gas.
A launch during a record cold snap in January 1985 gave engineers a scare.
Just a year before the Challenger launch in January 1985, when we recover these boosters, we always pull them apart and examine these joints. And this was the first time we noticed that we actually had this condition of blow-by in the field joint that we had observed. In fact, we saw it in a joint, one joint in each booster, the left and right. So there was 2 joints, very similar, that indicated that some gas actually got past the first O-ring, but stopped by the second one. That happened because at that time, that was the coldest launch we had ever experienced. And we determined that the O-ring temperature was about 53 degrees Fahrenheit on that particular launch.
Then, in April of 1985, NASA executed 2 launches in the same month for the first time ever. Again, engineers saw that O-rings had burned and eroded. It was an alarming trend.
Because we were lucky in that we had seen this behavior in the nozzle joint, not the field joint. Because had we seen something similar in the field joint, we all felt very uncomfortable that it would have leaked all the way out and caused a catastrophic failure. So we formed an O-ring seal task force right after observing this nozzle problem to look at all the sealing mechanisms, every one of them in the solid rocket booster, and see what we'd recommend to do.
They often ask me if I ever felt in danger, if I was afraid of getting aboard this atom bomb that was about to explode, given the accidents that had happened in the past. And my answer is absolutely not. And I don't think I'm an exception. No one who worked on the shuttle felt in danger. On the one hand, because we had been trained by NASA that took us every place where every part was built, allowed us to speak with every technician, and we realized that the system was incredibly strong, incredibly careful. Things were done with great care. And as far as I'm concerned, I almost came to feel that I was the weak link.
As NASA prepared to launch a top-secret payload from the shuttle for the Air Force in the summer of 1985, the team redesigned the rocket boosters to make them lighter and reduce the risk of O-ring failure, and made a proposal to NASA to fund the same changes to all rocket boosters used on the shuttles. But NASA rejected it. 7 of the 9 shuttle flights in the year prior to the Challenger explosion had shown warning signs that concerned engineers enough to write the memo to NASA. But their proposals were rejected. Few in NASA management wanted to slow the ambitious launch schedule. On the 28th of January 1986, one of the many complex systems failed, with catastrophic consequences for the crew and for NASA. 73 seconds into the flight, just when the shuttle was vibrating and flexing at its maximum, the flame broke through the seal and blew a huge hole in the external tank, aided by wind shear. The disintegrating external tank caused the shuttle to veer from its altitude, increasing the aerodynamic forces that ripped the shuttle apart. The boosters were thrown off, and the crew capsule catapulted toward the sea. Based on emergency oxygen supplies used on board and other manual switches turned on and off during their descent, the crew were likely alive and perhaps conscious for over 2 minutes until their craft tore apart upon hitting the Atlantic Ocean at 330 kilometers per hour. Alan MacDonald was on the failure team that sought to understand what went wrong.
When I was in the failure team at NASA, and I found the data that indicated had a problem with cold temperatures in the very joint that failed that kind of fit this puzzle. And the next question is, well, but even then it doesn't explain why it didn't blow up when I would expect it to blow up between 6 and 7/10 of a second. And so I asked immediately at that point in time, has anybody ever looked at the cameras of liftoff, not flight? And so they called down to the Cape, and the guy told me they'll pull one of those, and they pulled it. I says, make sure it's looking exactly where you see this fire coming out in flight. So I said, go find the one that's closest. And they did, and about 10 minutes later they came back to us, oh my God, we see a puff of smoke.
But if the O-ring failure was to blame, why did the shuttle not explode immediately, as engineers had predicted? They would later discover that after the O-rings vaporized, the hot gas of the burning aluminium oxide hit the cold steel and solidified right where the O-rings had burned, creating a fragile ceramic seal which held right up until the order to throttle up.
The winds aloft were so high that as the bracing strut that held the booster to the side of the tank became weaker, it tore the booster around on a pivoting arc and pushed the nose of the booster into the top of the 2 tanks, the oxygen tank. Already the flame coming through from one of the punctured segments that had overwhelmed the O-rings was operating like a blowtorch to open up the side of the very thin aluminium hydrogen tank. But when the booster pivoted and pushed in the nose into the oxygen tank, that caused a Roman candle effect, which was a great convulsive, it wasn't an actual explosion, not like a bomb going off. There was a great convulsive release of energy which punched the boosters off from the side of the tank and ripped apart components of the orbiter. The strongest part is the pressurized compartment, and that pressurized compartment remained intact.
MacDonald and engineers pored over the logbooks from the ice teams, but NASA managers said that the instruments had not been properly calibrated and increased all the temperatures they submitted to the Presidential Commission. Something was amiss.
Well, there's no doubt in my mind it was a cover-up. They covered up the low temperature data. They had tremendous pressures on their launch schedule, both from a political standpoint to support their out-year budget, and immediate ones to do what they already had on their plate, which was nearly impossible. And I think because of that, they did as much as they could to try to cloud this issue and make it sound more difficult and technical and hard to understand than it really should have been.
As NASA officials from Marshall Space Center were preparing their presentation for the commission, Alan raised objections and eventually put together a separate presentation of his own.
As part of the failure team, I started mentioning and questioning some of their conclusions and data, especially the cold temperature stuff, and that they were still looking at things that I thought were not only impossible, they're ridiculous. I said, if you look at the films, you can tell that can't possibly be, like lightning strikes and all kinds of funny things. And so I raised my hand and said, well, I made an assessment. I'll be willing to present something. And even stated that I really believe that a major contributor was whatever caused this cold temperature on this one joint. And that's why that joint failed and the other 5 did not. And I'm not a big believer of coincidences. And you could have heard a pin drop. There wasn't a single person supported me. There wasn't a single person that challenged me or a single person that offered another possible scenario what caused it.
A presidential commission, the Rogers Commission, was tasked with investigating how the disaster happened. Just weeks into the commission's inquiry, there were suspicions that NASA officials and contractors were not telling the whole truth. Commission member and famed theoretical physicist Richard Feynman turned their focus to the resiliency of the O-rings.
Well, I took this stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
At multiple hearings, MacDonald raised his hand and told the commission exactly what had transpired about how the decision not to launch got changed.
And I remember Neil Armstrong says, yeah, I think we need to hear from Mr. MacDonald to cause this meeting to be here in the first place. He says he has more to talk about. And I told him about all that transpired after it got changed. And I'll never forget, I could hardly keep composed, so I had done it. Dr. Sally Ride got up out of the bench, come running over to me, gave me a big hug and said, God, I'm glad somebody finally leveled with this commission. That took a hell of a lot of guts.
Upon return to work, however, MacDonald found he had been moved out of his prestigious engineering job.
And so what's my job? And they said, well, we're forming this new group on program planning, and your job's going to be head of scheduling. I said, scheduling? What the hell could I schedule? I don't build anything. What we build isn't what we have now. He goes, well, that's for you to figure out. It was clearly a non-job, hoping I would quit.
With time on his hands, Alan went to conferences in the field. At one event, one of the generals who was head of Air Force Space Command was surprised to see him and found out what had happened.
He said, you ought to be spending all of your time figuring out why the shuttle failed the way it did. I said, I'm not doing that anymore. He said, what do you mean anymore? You're a member of the failure team, aren't you? I said, I was, but I got taken off. You got taken off? When the hell did that happen? I said, I think it was exactly one day after I testified before you people. He said, you're kidding me. I said, no, I'm not. He said, well, that's bullshit. We'll fix that problem.
Alan MacDonald went on to join a super task force aimed at redesigning the shuttle to restore it to safe flight. The shuttle flew more than 100 successful flights after the redesign. The failure to stop the Challenger launch has become a case study for the dangers of groupthink, desensitization to risk, and the danger of putting cost-cutting and schedule deadlines over safety.
people that have to make good decision managers, and they're sometimes very tough decisions to make, should never feel comfortable that they've made the best decision unless they've used every tool in their toolkit. And the biggest tool they have in their toolkit is the brain power of the people they work with and work for them. And if they don't create an atmosphere where those people feel very comfortable to tell them issues or concerns that they may have, they've lost the most valuable data they can to make these tough decisions.
The failure of NASA to redesign or fix engineering problems when they were first raised led to a rationalization of grave risk as acceptable, especially when launch schedules and cost-cutting measures were bearing down.
But we were charging a fraction of what it was costing, and that was driving the upward momentum of launching every time on time. And that was the structural political beginning of the inevitable reduction of safety criteria. That's when we began to eat away at the edges of safety, and risk aversion became risk acceptability. And there were technical lessons and signs that were coming from even the very second shuttle mission that we could lose a crew on those boosters.
Managers have to be receptive to the concerns of engineers, who must be clear and courageous about reporting them. The pressure on the workforce to save money, time, and contracts ultimately cost 7 astronauts' lives and hastened the demise of America's space shuttle, which was retired in 2011. It remains to be seen if the US can overcome aerospace design challenges and political feuding to put women and men back into space from US soil once again, never forgetting the crucial engineering lessons learned from the Space Shuttle Challenger disaster.